This is Myra. She is 19 years old and she lives in Malawi, a developing country in Africa. Myra just had a baby. However, she had complications during her baby's delivery. Her labor was obstructed, and this caused a hole to be formed through the wall of her vagina into her bladder. This hole is called an obstetric fistula, which is a childbirth injury that severely affects a woman's life. It can cause urinary incontinence, chronic infection, social isolation, and depression. You may not have heard of it because it is preventable in the developed world. Yet, this condition impacts 2 million women worldwide in areas where women have poor access to proper labor and delivery care. Because of this, they are unable to have a C-section to resolve an obstructed labor like Myra's. Myra was one of the lucky ones who was able to travel a long way to a hospital to have her fistula surgically repaired. However, even after the surgery, Myra noticed that she was constantly leaking urine. This is a condition called urinary incontinence. She told her doctor about it, and he explained that the muscles of her urethra had been so damaged that she would never be able to control when she urinated. Myra would leak urine for the rest of her life. Myra was so ashamed of her condition, she became housebound and could not hold a job. Myra is not alone in suffering from obstetric fistula-derived urinary incontinence. About 40,000 other women in the developing world face the same issue. In addition, approximately 200 million women suffer from urinary incontinence worldwide, derived from old age, stress, and other factors. The global urinary incontinence device market in 2016 was valued at $1.6 billion and continues to rise.
Myra asked her doctors what her options were. Unlike people in developed countries, Myra has limited access to health care and limited options to control her incontinence. These options include an absorbent pad, an intermittent catheter, or a urethral plug. Wearing an absorbent pad is discreet, but is not a sustainable solution because Myra does not have regular access to the appropriate vendors or the economic stability to pay for pads for the rest of her life. Continual catheterization often leads to infection, would be difficult to acquire in a developing country, and would only minimally increase Myra's quality of life. There used to be a device on the market called a urethral plug that is discreet and durable. However, this device was not appealing to people in the developed world and thus did not have enough funding to support continued distribution in countries like Malawi.
This is where we stepped in. Our team of biomedical engineers learned about this problem and thought, there must be a better way. So, we sought to create a solution for women with urinary incontinence that was low cost, minimally invasive, and feasible for women in both developing and developed worlds. Our design must have a simple mechanism with minimal parts, be discreet, reusable, and last over an extended period of time. The aim is to give women control over their urine flow, prevent infections, follow up doctor visits, and keep a low maintenance cost for women in these low resource settings. With that in mind, we began designing. We viewed the urethra as a leaky pipe that needed to be fixed. We first drew inspiration by looking at different valve types used in plumbing. Through our research, we found something similar to a needle valve would be the simplest way to stop the dripping. But our biggest question was, how do we open and close a valve hidden in the urethra? We considered 3 valve options: a conformation activated valve, a magnetically activated valve, and a click to open valve. We down-selected to the click-to-open valve design and created our first prototype. After building this design, we found that the device was much too complex and had too many moving parts to fit into a small confines of a 5mm wide urethra. We then drew new inspiration from a deodorant screw mechanism and pivoted our design to create a mechanically activated screw valve that is inserted into the urethra and activated from an external knob. Our first iteration of this mechanism included a flexible flanged anchor, which we prototyped by 3D printing the base and molding the flange out of silicone. After collecting feedback from a group of urologists, we changed the insertion method to mimic the shape of the urethral plug. Our new anchor design was a smooth bulb, which was slits on the side that allowed for urine to flow through the device and increase the ease of use. This improved the overall quality of the device, and this is our final proposed iteration to prevent urinary incontinence. So now, a woman like Myra can simply insert our device into her own urethra and it serves as a plug. The device is anchored in place with an internal anchor located at the bladder-urethra interface and an external anchor with urine outlets and a turn knob located at the end of the urethra. As Myra goes about the day, her valve remains closed, preventing her from evacuating urine. When she needs to void her bladder, she can turn the screw valve, which allows the urine to flow through. She can wait approximately 1 to 2 minutes until all her urine is voided and then twist the knob to close the valve again and prevent further urine leakage. When the device needs to be cleaned, the user can simply pull out the device, boil it, and then place it back in her urethra, all without a doctor's visit.
Using our prototype designs, our team filed for a provisional patent before presenting our device at an obstetric fistula conference to a team of urologists in New York City, at which the doctors expressed promising interest in our design. When we tested our first screw valve design, our test results showed that our design was able to hold 500 milliliters of water without leakage, proving that it would withstand the pressure of urine in the bladder. Further, our device exhibited a flow rate of approximately 10 milliliters per second. This exceeded the urine flow rate goal of 6 to 8 milliliters per second, given to us by a panel of urologists, which are based on standard times to void a bladder. However, our initial prototype was not made to scale with an inner valve diameter of 3.5 millimeters as opposed to the actual size of 3 millimeters. Based on these results, the projected flow rate of a 2-scale inner valve would be approximately 7 milliliters per second. In vivo and in vitro testing using accurate models of the human bladder pressure will be done to confirm this as well.
In the future, our design team plans to create prototypes to the scale of a human urethra for more testing. This will be conducted to evaluate the flow rate, maximum seal pressure, and removal force of the device. Validation studies will then be done in a porcine model to evaluate the safety and efficacy of our design for use as a urinary incontinence device. In summary, our team's novel device is a promising treatment for women with all kinds of urinary incontinence, especially for women that are in low-resource settings who had obstetric fistula repair. With this device, we believe we can change the lives of women for the better and allow them to return to their everyday lives without concern for involuntary urination. At the same time, it also has the potential to help women from developed countries. Our team would like to thank everyone that helped us in our design process: Texas Children's Hospital, the Beeman Department, and especially Dr. Julie Hakim and Dr. Rachel Pope for providing feedback and guidance throughout our design process. Let's hope that one day this device can help the women who need it the most. Thanks, and Gigan.